Hey everyone, welcome back to TheCodeQuant. Since this is my first quantitative finance project, I wanted to try something ambitious. We are building a reinforcement learning trading bot. Here's the challenge. In quantitative finance, there is a famous formula called the Black-Scholes model. It uses heavy calculus to tell you exactly how to hedge an option to remove risk. It's the holy grail of mathematical trading. So this is how we start. Basically, first of all, we have to download a few libraries. We need NumPy for our math operations, standard stuff. We are also importing Gymnasium. If you're from a data science background, you might know OpenAI Gym. Gymnasium is the maintained fork of that. It's the framework that lets us create a video game market for our AI to play in. We are also using Stable Baselines 3. This is a lifesaver. It contains pre-built reinforcement learning algorithms like PPO, so we don't have to code the neural network from scratch. And finally, SkyPy is here so we can calculate the true Black-Scholes price to check our homework later. Before we unleash the AI, we need a benchmark. We need to know what the perfect mathematical answer looks like. That's what this function, Black-Scholes price, is doing. It takes the stock price, strike price, time to maturity, risk-free rate, and volatility. It calculates D1 and D2, which are probability factors, and returns the fair price of the option. But more importantly, look at this second function, Black-Scholes chart delta. In the world of hedging, delta is key. Delta tells us how many shares of stock we need to buy to neutralize our risk. If delta is zero point 0.5 and we sold one option, we need to buy zero point 0.5 shares of the stock to be safe. Our AI will never see this function. It has to figure out this delta value on its own. Now let's build the arena. I'm creating a custom environment called HedgingInf. This inherits from Gymnasium. In the init method, we define the rules of our market. I've set the stock price to start at 100, the strike at 100, and volatility at 20%. We are simulating one trading year divided into 252 steps, basically one step per trading day. Visual, highlight, self-trans, cost, Josher 0.01. Here's the kicker, transaction costs. I've set this to 1%, which is actually huge. I did this on purpose. If the AI trades too much, it loses money. If it doesn't trade enough, it faces risk. It has to find the perfect balance. Math formulas hate transaction costs, but RL agents adapt to them. Visual, highlight action space and observation space. For the action space, we use a box. This allows the AI to output a continuous number between 0 and 1. This represents our hedge ratio. What percentage of the stock do we want to hold? For the observation space, the AI gets to see three things: the current stock price, the time left until the option expires, and how many stocks it currently holds. Now the step function. This is the heart of the simulation. Every day, the AI chooses a target holding. We calculate the cost of that trade, update our portfolio, and then we move the market. I'm using geometric Brownian motion to simulate the stock price. This line with np.exp and random.normal generates a random walk for the stock, just like in real market theory. Now, how does the AI learn? It learns through the reward function. In reinforcement learning, you get points for good behavior and lose points for bad behavior. In this specific code, I've set the reward to be negative based on the transaction costs. This forces the agent to be extremely efficient. It's trying to minimize the pain of trading fees while surviving the market volatility. It's a simple reward structure for this first version, but it teaches the agent not to overtrade. With the environment built, training is actually the easiest part thanks to stable baselines. I am using PPO, or Proximal Policy Optimization. It's the industry standard for these kinds of continuous problems. We initialize the model, pass in our hedging NV, and tell it to learn for 10,000 time steps. In a real production environment, we'd run this for millions of steps, but 10,000 is enough to see if it starts to understand the logic. Once the training is done, we have to test it. I wrote a loop that runs the simulation one last time. It records what the AI thinks it should do and compares it to what the Black Skull's math says it should have done. And here's the result. The black line is the stock price moving up and down randomly. The red dashed line is the perfect math, the black Scholes delta. The blue line is our AI agent. For the next version of this project, I plan to add a more complex reward function that penalizes variance more strictly and maybe add real market data. If you're interested in AI and finance, make sure to subscribe to the CodeQuant. I'll be dropping the GitHub link for this code in the description